Section 3.5 on exponential and logarithmic models. So in this section we're going to be looking at real-world problems or word problems that use exponential and logarithmic equations. So this first set is called growth and decay, and you use the equation y equals a times e to the bx power, where a is the initial amount of the object, whether it's people or animals or bacteria. B represents the rate of growth or decay. If it's a rate of growth, it's going to be a positive number. If it's a decay, it will be a negative number. X represents the time period, which could be days, months, years. And then Y equals the amount of that object, people, animals, bacteria, after that specific time period. And we can be solving for any one of these variables when you're given this equation. The next three, the Gaussian model, the logistic model, and the logarithmic models, are all different forms that exponential and logarithmic equations can look like. And a lot of times if it's a Gaussian model or a logistic model, they're going to give you the equation in the problem, and then you're just going to have to solve for a missing piece. Okay, next is the compounding interest formulas. So the first formula, A equals P times 1 plus R over N to the NT power. This formula is used if they give you a specific number of times that the interest is compounded throughout the year. So they're going to tell you annually, semi-annually, quarterly, or monthly, or some sort of time frame, and you need to use that formula. If they say that the interest is compounded continuously, then you're going to use the second formula, A equals P times e to the RT power. And when it's compounded continuously, that just means that it's constantly calculating the interest. And it's very close to being calculated on a daily rate, but it's actually a little higher than a daily rate. Okay, so let's look at these examples. So in example 1, I have the population of a large city is modeled by this equation, 1.8 times e to the 0.026x power in millions, where x equals 0 corresponds to 1990. They want to know what year the population exceeds 2.5 million people. Okay, so this is an exponential growth or decay problem. It's growth because the population is going to increase. And we use the equation y equals a times e to the bx power. Y is going to equal the amount that we're trying to get in over a certain amount of time. We're trying to see when the population is 2.5 million. And they gave us the rest of the equation in the problem. So I substitute these in, and 2.5 is supposed to equal 1.8 times e to the 0.026x power. So our goal is to solve for x, which represents the years since 1990. So first step, we need to divide by 1.8 on both sides. And I'm going to wait and do all the calculations at the end so I don't have to round numbers throughout the problem. So I'm going to leave this as 2.5 divided by 1.8 equals e to the 0.026x power. So if you remember from earlier in the chapter, we need to bring the x down out of the exponent. And the only way we can do that is to take the log or the natural log of both sides of the equation. For this problem, I'm going to use natural log because there's a base e in the problem. So I take the natural log of both sides, and on the right-hand side, the exponent comes in front of the natural log of e. And you'll remember one of our properties is that the natural log of e is equal to 1. So that natural log e just goes away. It's like being multiplied times 1. So now I need x by itself. I'm going to divide by 0.026 on both sides. So in my calculator, I would type the natural log of 2.5 divided by 1.8. Make sure you close parentheses, and then divide by 0.026. So if you type that into the calculator, you're going to get that x is about 12.63. So you always want to think about the answer that you got and how that corresponds to the question that they asked. They said, in what year, blah, blah, blah. So this has to do with a year since 1990. So I'm going to take 12 years and I'm going to add that to 1990 to give me 2002. If I rounded it up to 13, then the population would have been higher than 2.5 million. So I just left it at 12 years. Okay, example 2 says that 2 hours after bacteria were introduced to a culture, the population was 256. 5 hours later, the population was 541. And they want to know what the population will be 24 hours after the start. Okay, so again, this is an exponential growth problem. So we're using y equals a times e to the bx. And I went ahead and plugged in for the starting information that they gave me. We know that 2 hours after bacteria was introduced, the population was 256. So after 2 hours, there was 256 of this bacteria. We don't know the initial amount, A. And then times e to the b times 2 power. B would be the rate of the growth or decay. We don't know that value. And then 2 because it was 2 hours later. So I've got two things missing in this problem. What I'm going to do is go ahead and solve for A and use that on another part of the problem. So if I divide by e to the 2b power, this is an equation that I can use to calculate A in a second. Now I'm going to go to the second statement that said 5 hours later the population was 541. So it's 5 hours after the 2 hours. So I'm going to say that 541 equals A, my initial amount, which we just rewrote an equation for A that it was 256 over e to the 2b power, times e. This time I put a 7 there because it was 5 hours after the initial 2 hours. So altogether we're 7 hours later. Now when you have something on the top and bottom of an equation, that e to the 7b over e to the 2b, that will reduce to e to the 5b. So now what I can do is I can solve for b and find out the value of the rate of growth or decay for this bacteria. So I'm going to divide both sides by 256. So when I divide by 256, I'm going to have 541 over 256 equals e to the 5b power. Now I need to take the natural log of both sides to be able to bring the exponent down in front of the e. So that's going to be the natural log of 541 over 256 equals 5b times the natural log of e. And I remember that the natural log of e is 1. So then all I'll have to do is divide by 5 on both sides. So natural log of 541 over 256 divided by 5 will give me the value of b, which is the rate at which this bacteria is growing. So b turns out to be 0.15, and this is just a percent. I could move the decimal over and it would be 15%, but I want to leave it as 0.15 because I'm about to plug it back into a formula. So now that I have the rate at which this bacteria is growing, I need to find the initial amount for the bacteria. So that's our A equation that we had earlier. So I plug in B in for A. 256 over e to the 2 times 0.15 power. Type this into the calculator and it turns out that A is 189.65. So when this bacteria started growing at time equals 0, there was 189.65 units of it. Whether it's grams or milliliters, we don't know. 2 hours after that, the value was 256, I believe. And then 5 hours later, it was 541. And then now what they want us to do is find out how much bacteria there is after 24 hours. So now that I know the rate and the initial amount, I can plug those into the original equation and find out how much bacteria there will be after 24 hours. So y equals 189.65 times e to the 0.15 times 24 power. 189 is the initial amount, 0.15 is the rate, which is b, and then 24 is the time, 24 hours after the bacteria was introduced. So when you type all this into the calculator, you get 6,941. So you can see the bacteria is not growing at a constant rate. It's not going to go up by the same amount every time. That would be a linear function. This is exponential, so the rate, or the constant value is not the same. It's going to change each time that it increases. Okay, number 3 says that a radioactive isotope, radium, has a half-life of 1,620 years. If the original amount was 5 grams, how much would remain after 10,000 years? So when something talks about a half-life, that is the amount of time that it takes for that object to be reduced by half of its weight. So if it started with 5 grams, its half-life, it would have 2.5 grams left over. And that's going to take 1,620 years for this radium. So what I'm going to do is plug into this formula. The 5 is the initial amount times e to the b times 1620, because that's our time, equals 2.5. Since it's half-life, that's how much remains later, is half of its original weight, which is 2.5. So now we're going to solve for b so that we can plug back in a second and find out how much there was after 10,000 years. So I'm going to divide by 5 on both sides. 2.5 divided by 5 is 1/2. 1/2 equals e to the 1620b power. So I need to take the log or natural log of both sides. Since there's an e, I'm going to use natural log. So natural log of 1/2 equals 1620b times ln e. And remember that ln e just turns into a 1. Then I'm going to divide by 1620. So natural log of 1/2 divided by 1620 is going to give me my value of b. Now on your calculator, it probably gave you a weird number like -4 point something something something, and then a capital E to the -4. All that is scientific notation on your calculator. So you just move that number over 4 spaces to the left, which gives you -0.0004. So this is our rate of decay for this isotope. So now that I know the rate, I can plug in the information that I was given to find out how much there will be after 10,000 years. So y is what I'm solving for, equals my initial amount 5 times e to the -0.0004, which is my rate, times t, which is 10,000 years, my time. So when I type this into the calculator, I get 0.092 grams. Now, depending on how you type this in the calculator, if you rounded like I did on this b value, then you're going to get 0.092. If you kept the number that was in the calculator and just inserted your answer in there, kept the whole number that was in there, you probably would have got a different answer, and I think it's like 0.06 something. So I'm going to be able to determine that you were close to your answer if it's in between those values somewhere. Okay, number 4. Says that the State Game Commission released 100 animals into a game preserve. The agency believes that the carrying capacity of the preserve is 1,200 animals. The growth of the herd is modeled by this equation, where t is months. They want to know how long it's going to take the herd to reach 1/2 of the preserve's capacity. So we're starting out with 100 animals. We don't know what type of animals these are. The preserve will be at capacity when there are 1,200 animals. And they want to know how long it's going to take for them to reach half capacity. So that's 600 animals. So we're going to put 600 in place of the P of T. That's the population with respect to time. We're trying to figure out how long it's going to take for there to be 600 animals on the preserve. So 600 equals 1,200 over 1 plus 8 times e to the -0.1588 t power. So since 1200 is being divided by all that craziness down at the bottom, and that's where the variable is, then I need to multiply by that on both sides. So 600 times 1 plus 8e to the negative 0.1588t power. Then I'm going to divide by 600 on both sides. And we know that 1200 divided by 600 is 2. So our goal right now is to get the e by itself. So we're going to subtract 1 on both sides. And then we'll divide by 8 on both sides. So now e to the negative 0.1588t power equals 1 over 8. So again, to bring the exponent down, I need to take the natural log of both sides. And this time I didn't write the natural log of e because I know every time I see natural log e that it equals 1. Okay, so to get t by itself, we need to divide by negative 0.1588. So in my calculator, I'm going to do the natural log of 1 over 8 divided by negative 0.1588. And we get that t is approximately 13.095. So then I think back to what this is talking about. This is talking about the number of months that it takes for the population to be 600. So that's just going to be 13 months. We're not going to use the decimal portion of this number. Okay, last example, number 5, says what is the interest rate on a savings account given the following? The amount invested is $100. The current value is $2,500. It was compounded monthly for 20 years. So we're going to use our compounding interest formula, and we have to use the first formula because it's compounded monthly. If they said compounded continuously, I would use the PERT formula. So I've gone ahead and plugged in everything that I know. My amount after time is $2,500. My principal amount or initial amount was $100. I don't know the rate. It was compounded monthly, so my N is 12, and my time is 20 years. So our goal is to find the interest rate to get R by itself. So first thing I'm going to do is divide by 100 on both sides. So 2,500 divided by 100 is 25, equals 1 plus r over 12 raised to the 240 power. So I have to undo the 240 power. So the opposite, or the inverse, will be to raise it to the 1 over 240 power. So I have to do that to both sides. On the left, 25 raised to the 1 over 240. I'm just going to leave that. On the right-hand side, the 240 times 1 over 240 is going to cancel. So then we're just left with 1 plus r over 12. Then I can subtract 1 on both sides. And since r is being divided by 12, the opposite would be to multiply by 12 on both sides. So I've got 25 raised to the 1 over 240 power minus 1, and then times 12. So when you type this in the calculator, you're going to get something like 0.162. And this is an interest rate, so I need to move the decimal over 2 places to the right. So my interest rate is going to be 16.2%.